During this video we're going to take a look at LoRaWAN, which is a long-range wide area network, and the LoRa physical layer. First thing we have to understand is, why is there a hunger now within the process industry for wireless sensors? And it's really to monitor assets that wouldn't conventionally be wired back to a PLC or DCS system. So there's no feedback on how well they're performing. And these mechanical assets can fail. If we have a look at a steam trap, industry reports tell us that these devices have a failure rate between 5 and 28% a year. And the failure mode can either be blocked or leaking. So if you're leaking steam, you're losing money. If it's blocked, you have condensate working its way back into your steam system, so you can have cold condensate hitting hot steam during the startup phase, and this can cause thermal shock and damage. The catastrophic side would be if that cold water hit a turbine blade, steam turbine blade, at the same time as superheated steam hitting that. That could potentially completely break the turbine. So a small mechanical asset failure can have catastrophic outcomes. And we wouldn't conventionally run wires to these because the costs are too high. We do want to monitor them, but we need something that's going to need no wiring. So ideally battery powered with some sort of wireless communication. So let's take a quick look at the wireless technologies. Starting at the bottom for the shortest range is RFID and near field communication. Relatively uneasy to say. An example of near field communication is your phone. You use your phone for contactless payments, and we only need that to work over small distances and send a small amount of data at any time. So ideal for those scenarios. So we need to move up in the spectrum, and the best solution for bandwidth, so getting the most data, is Wi-Fi. We're all familiar with that at home. We're watching movies, high definition movies, 4K movies over Wi-Fi, but it's very, very power hungry, and it doesn't have a relatively long distance when it comes to process industries such as oil and gas, pulp, paper, chemical, which have multiple obstacles. Sitting underneath that with a lower bandwidth but still relatively good is Bluetooth, so we can listen to music over Bluetooth. We wouldn't necessarily start thinking about streaming a 4K movie, but it's still good for data transfer. And again, the range is less than Wi-Fi. Very skeptical when somebody tells me that Bluetooth can work over 200 meters. My message to them is, go and try it in an industrial environment, and you'll probably be lucky if you get anywhere close to 50 meters. So we need something that is going to have range and low power. So a technology that complements Bluetooth or sits by the side of it is Zigbee. This is designed to have a mesh network, so it claims to have line of sight distances 10 to 100 meters, but each sensor can be used as a repeater. That can cause latency issues, and we need to position our sensors around so we can create that mesh network. Now, Bluetooth have sort of fought back. You can get Bluetooth mesh networks using Bluetooth Low Energy, but they're complicated to understand. The other problem with these two sort of communication standards, the protocol that sits behind them isn't brilliant with regards to security. Yes, you can have encryption, but there's no real industry governing body sat behind it, and there is sort of, but it's not being pushed as a must that you must have this type of encryption, this type of password authentication. It's really dependent upon the developer. So cellular comes in next. Really, that would be the answer to everything. It's high bandwidth and long range, extremely long range. The problem is, you'll be aware with your phone, you can't have it on all the time. Your phone, if it was transmitting or you're watching a movie using your cellular connection, I know the screen takes a lot of the power, but you would lose battery power relatively quick. We're after batteries here that are going to last 3, 4, 5, 6 years, not 2 months. We can't be in that territory. So we need something else. So there is something, and hopefully it makes sense. It's a low power wide area network. Now, we're not actually talking about what it actually is at the moment. This is just a concept, but you have a long range, in some cases up to 17 kilometers, but very, very low power. But what that means is we sacrifice bandwidth. Now, when it comes to predictive maintenance monitoring, we don't really need the bandwidth because we're not using these sensors to detect an immediate fault. We're using these sensors to record data over time and trying ideally to predict and stop the fault from happening. So this sort of fits in nicely to what we're trying to achieve. Let's take a look at the 3 technologies that we can use for low power wide area network. Let's start in the middle. Narrowband IoT. Based on SIM card technology, I thought this was going to be the answer for everything. It fits very well with technologies where you are recording a lot of data over the day, you have some sort of internal storage, and you send that data out once a day via another secure method, such as File Transfer Protocol, FTP. The communication is governed by the license spectrum, which is operated by the telecommunication companies, and it has a complex protocol which really hasn't established itself in the way that, say, LoRa has. It has its place, but for vast implementation, so if we were going to talk, say, about a site with steam traps that could have 500 steam traps, this may not suit that type of application. Where these two, Sigfox and LoRaWAN, could. We have 2 technologies that use the unlicensed sub-gigahertz spectrum, which is very good for getting around metal obstacles. And this unlicensed band is referred to the ISM band, so industrial, services, and medical. So they're very, very similar. The modulation is where it differs. So you've got chirp, spread, radio modulation, which means that we can almost operate below the noise floor. And then FSK, I can't remember what that means, but it's going to be frequency shift something, radio modulation. They're very good, both of them, but really the one that's sort of winning is LoRaWAN. And that's because there's more and more public networks becoming available than what there is for Sigfox. I'm not saying Sigfox is dead and is not the way to go, but really, definitely within Europe and probably North America, it's a well-established network. So why does this sub-gigahertz signal work so well in our application? This is not a very good slide, but hopefully it makes sense. So when you have a high frequency, you have a tight signal that tends to bounce straight back towards you. But when you're trying to get your signal out to as wider area as possible, you want a signal that's got a wide beam. And this low frequency spectrum has that. So if we had a look at this animation, which isn't great, I admit, we get this spread. What happens with these low frequency signals? They tend to bounce off the obstacles. Now, it's not this easy. There's quite a bit of science behind this. We have to have our gateway positioned so we don't have the first rebound off an obstacle too close to the gateway. It's not as simple as what I'm showing you, but it works very well at bouncing off obstacles. It's not completely immune to the pipe work, but it tends to work a lot better in these built-up areas. So over the next few slides, we're going to build a story around what you can see in front of you now. So this is sort of the network architecture, but we need to understand the data flow. And the really nice thing about LoRaWAN, it's got end-to-end secured payload. So from the sensor all the way to our cloud application. The main 3 elements we're going to look at are obviously the sensors and how they're designed, the gateways, what function they perform, and then the network server, which is some software on a PC or in the cloud that controls this data traffic and the security elements associated with the whole LoRaWAN architecture. The beauty about a LoRaWAN network, you can have a private network or a public network, and it doesn't matter what type of sensor you've got. You may have something for measuring pressure, something for measuring temperature. The gateway and the network server can cope with routing all of those different types of sensors, but they need to comply to standards, and this is where LoRaWAN sort of ticks the box against other protocols. So let's have a look at how this LoRaWAN sensor is designed. So the first part, we have to have a look at the application. So this is what we're measuring. Is it temperature? Is it pressure? Is it flow? What power requirements do we need? How are we powering the sensor itself? Is it going to be battery powered, energy harvesting? Does it actually need power? Can we get power from 24 volts or 230 volts AC? So those things are pretty standard for sensor designers and even instrumentation people. Then we need, what approvals do we need? Is it ATEX, CE? All of that needs to come into play. And then we have the sensor options. And this is important because we now are going to be looking at low power. We need to make sure we don't spoil the whole thing by putting a high power sensor option in the application layer. So there's some nice digital communication protocols such as I2C and SPI that have very, very low power requirements with digital communications over short distances. This will be reading the process data. That process data is often referred to as metadata at this point. So let's take a look at the next layer. The next layer is referred to as the MAC layer. If you want to develop a sensor, you have to approach the LoRa Alliance and get it tested and everything else in accordance with their procedures to be able to put the LoRaWAN or LoRa Alliance stamp on your product. There's quite a lot that the protocol sort of governs, but it governs how often the device goes to sleep. So Class A is a battery powered device. We do have two-way communications, and I'll just use this as an example. So it will wake up every 2 hours, or if you've programmed it to send an event on it, on an alarm, it will send that information, and then it stays awake for a little bit longer to see if there's anything coming from the master, which could be the application in the cloud, to say, right, are you sending me anything? It could be a software update, or it could be a command to get more information. It only keeps that awake for a shorter period of time, and then it goes back to sleep mode, where it's just measuring the process value. B is a variant of that, but it wakes up a bit more often. And C is where you've actually got more power. It could be that you're energy harvesting, or you've got 24 volts. So it keeps that receive window open all of the time, apart from when it's transmitting data. So it can't do full duplex communications. It can only do one or the other. It also defines how it joins to the network servers, and it has standards, what we call MAC commands. So standard functionality, you can send a command from the cloud, for instance, to synchronize the time on the device. We also have some really nice features, such as firmware update over the air. So this is good because now you're deploying hundreds of sensors. If you do need to upgrade the firmware, that is covered as part of this MAC layer. So think of it like the protocol, and don't forget LoRa Alliance is really the governing body behind these standards. And the last layer is the physical layer, and this is the LoRa part of the sensor. We talked about the ISM band. Now this is probably the one weakness of LoRaWAN. It would be nice to have one ISM band that covers the globe, but unfortunately you can see here the EU has two that you can use. Quite often we're using 868. The US has something else, then Australia. India has a very similar band to the UK, but it's just slightly different. So we have to make sure that we don't sell sensors to a region where you can't use them. And then in the background we also have fair use policies. Let's have a look at this little table here. This is important with LoRaWAN. It has something called automatic data rate. The sensor will transmit at the slowest speed. Why do we do that? Let's use an example. You want to talk to somebody in a noisy environment. There's two things that you can do. The first thing is you can shout. Well, we can't shout because the amount we're allowed to shout is governed. I think it's 14 decibels. So we can't shout any louder than 14 decibels. The next thing that we can do to try and make ourselves heard is we can speak slower. And that's referred to as the spreading factor. And you can see here, spreading factor 12 is the slowest, and it covers longer distances. It can go up to 14 kilometers, but we have very, very slow data rates, and we have slow time on air. The fair use policy, I'm doing this from memory, I think is 30 seconds a day per sensor. Can't keep transmitting data all of the time because you're only allowed to be on air for 30 seconds per sensor. However, for an industrial environment, we don't really need to go to these stupid distances. Maybe in the water industry, where I've seen some examples that in the UK a certain water company is using LoRaWAN for monitoring your water usage in your house. Yeah, that makes sense. We want large distances, but we've got very, very small data packs. But for process industry, spreading factor 7, 2 kilometers with a time on air of 56 milliseconds. There's a very good tool here that you can use, an airtime calculator. I'll cover this on another video just to give you a demo of it, where you can put in how many bytes of data you're transmitting and how much time that will take on air, and then how many times you can retransmit that during a day. But this is the important thing. These fair use policies differ again for each region. So you have the frequency, but also the fair use policy. Now, when you're developing a sensor, what you try to do is find the region that's got the worst fair use policies, make sure your device works there, and then when you roll it out into the EU, which has got relatively flexible fair use policies, you know it's going to work. I think the US is probably one of the worst for the fair use policies, so you develop your sensor to that. So I hope that makes sense. So when you bring it all together, you have your three layers, you have your application, you have your MAC layer, which is governed by LoRa Alliance, and then you have your physical layer, which is the LoRa part of the sensor. That is all controlled, and as I said, if you want to have these trademarks, you have to use the LoRa Alliance to assess your sensor. There's test tools that you can use, and you have to tick those boxes. So it's a bit like being registered on Profibus International. You have to make sure that your device complies with the Profibus standards. This is what we're looking at here. This next part, the gateway, is probably the best thing about LoRaWAN. When you're building a wireless infrastructure, the gateways can add complexity. Let's take a look at a couple. Bluetooth, when you first look at this, it looks great. It transmits a lot of data. But the processing power of the gateway is a limitation. So a lot of gateways are limited to 8, 10, 15 sensor connections per gateway. Then wireless HART. Again, wireless HART on paper looks fantastic. But unfortunately, the wireless HART gateway is limited to 20 connections. And it costs about £4,500. It is suitable for Zone 2, but for every gateway, you need power and you need an Ethernet connection. So now your installation costs go through the roof. I call this gateway complexity. With regards to LoRaWAN, we can have thousands of sensors connected to one gateway. I wouldn't recommend putting all of your eggs in one basket. Sorry, that's a UK saying. So we try and split and move your gateways around the site. But this is going to be discussed how the sensor connects the gateway in a minute. The output to the gateway is called the backhaul. So let's have a look at this in more detail. The gateway, first of all, needs to adhere to the regional parameters. We've already discussed that, so the ISM bands, etc., etc. It does require power, but I have seen, I can't remember where I've seen it, that somebody is developing a battery-powered LoRaWAN gateway, which would be fantastic. But it does need a backhaul connection. This backhaul connection is the connection from the gateway to the network server that can either sit on premise, on a PC, on a virtual machine, or in the cloud. And there's various connections, you can see them there, 4G, Wi-Fi, RJ45, or even satellite. The next thing is the number of channels. So this is the number of receive channels. It's different to the number of transmit channels. So the gateway can have 16 channels. That's probably quite an expensive gateway. Most of the time we have 8 receive channels. To send data from the cloud down to the instrument, we've only got 1 or 2 channels. So you just have to bear that in mind. It's not the same for transmitting as what it is receiving. The data is always transmitted at 14 dB. We try and use high gain aerials where we can. So you can see here on this example, there's the gateway, there's the power, the backhaul connection is probably some sort of wireless connection on this, and then we have the aerial. The important thing about the gateway, it never stores any data with regards to process information and customer information from site. It's purely a gateway, as the name suggests. So we don't need to program anything on this. Ideally, it needs to be installed as high as possible, and the gateway will not automatically join the network. The security and how the gateways join the network is governed by the network server. All data that flows through the gateway is 120-bit encrypted. So let's take a look at the network server. So here, the whole LoRaWAN server consists of a join server, a network server, application server, but this middle bit is the section that controls the gateways and the flow of traffic. You can have multiple gateways at multiple locations. Right? It doesn't matter. We would recommend having at least 3 gateways on one site, because what it can do with 3 gateways, it can actually triangulate and tell you where the sensor is installed on your site. But let's have a look at this in its most simplistic form. Again, sorry about the quality of the presentation. The gateways have now been registered, and the sensor is now sending out its request to join a network. It's not sending out any process data. It's going, hello, I have an ID, and in this case we're calling our ID Fred. Can I join your group? The network server will receive that information from all 3 gateways. So all the gateways can hear Fred. It's in range. But we don't want to keep having the same message coming from 3 gateways. So this is now where the network server kicks into action. As you can see, it says stop talking at once. I want to see who's the most reliable. Now, what you'll get as part of the message, you'll get a signal strength and signal to noise. So an RSSI signal and an SNR signal. The network server looks at that and establishes what is the most reliable path to the network server. So it's saying, right, okay, that sensor, the best path is through this gateway into the network server. We still haven't joined anything. It's just said, right, this is the best communication path. Now, if somebody turns that gateway off, or it blows up, or it blows away in the wind, whatever, doesn't matter, this network server again will kick into action, and it may be now that this gateway is the best route to go because this gateway has disappeared. So it automatically does all of that in the background. You don't have to program it to do it. It will sort itself out. There are some nice roaming functions as well that you can do, but we're not covering those in this presentation. So now Fred needs to find the group, and this is where the application server now comes into action. On the application server, we need to tell it that this sensor, Fred, belongs to an application. They all are listening and saying, right, okay, I'm aware of Fred. He belongs to this group. And the other ones are saying, well, I don't know. So they're not programmed to recognize him. So now we have something on the network that knows what it is. So how does that work in real life? This is an example of a sensor, and you can see on the sensor you have this EUI code. So this is one of the codes that we need to program into the application server, and this is a screenshot from the application server in the cloud or on premise. Here you can see the join and device EUI keys stored on the sensor. The application key is generated on the application server, and that is then sent to the instrument to align all three codes as part of the initial security check and the join procedure. So what happens next? We have the codes programmed into here. Fred has his three join codes, which we've just said. The application server has those programmed up, and now what it does is it generates something called a session key. And these session keys, I think, are 32-bit. There's two of them, and again they're 128-bit encrypted. It sends those session keys to the sensor, and the sensor stores those on something called a crypto chip. And this is something that's been developed by Semtech, and they're sort of one of the co-founders of LoRaWAN, and it stores those encrypted, so they're always on that device, so we don't have to go through the join procedure again. Now we are ready to start transmitting data. We have a secure connection. We've generated these session keys. The other thing that it does, the application server, it tells the sensor to set, there's two count values, there's one for transmit, there's one for receive. It says set those to 0. This is really important. So every time that I transmit data, this sensor will increment this count value. The application server knows that it should be seeing a count value of 20 during the next transmission, because the previous one was 19. The important thing here with the application server, no data is stored. So let's have a look. There's some rules again that are defined in the MAC layer of the instrument with regards to the crypto chip. I've got an example here. This is LoRa IoT. This is an application server for, it's not there anymore, so don't think you can copy these, but you have your session keys. So these are the session keys that you would generate via the application server, and they're sent, so you can see here you have a network session key, an application session key. They're sent to the sensor. And there's some rules. You can actually on here program so you can't see these on the application server. There might be different login levels, but here I'm showing them. Again, don't forget they're sent to the sensor, not in this format. They're encrypted 128-bit. The session keys must never be copied. The session keys must be stored on the end device on an approved crypto chip. Again, this is where the standard is really good for security. And you should never read those session keys either electronically or over the network via Bluetooth. So that's the application layer talking to the sensor. The next part of the application layer is to push the data into our web application. Now what's really important, the application layer doesn't store any data. It's not a database. It's a funnel. It will store a small amount of data for diagnostics purposes, but it won't store months and months of data. That's where you need to have a database connected to this. It doesn't store any data. It really has no capacity to do any alarm functionalities or anything clever. It's just pushing the data to an endpoint. And the endpoints vary, and I've just got an example again. This is from LoRa IoT. So the one I tend to use a lot is IoT Hub, but you could push that to AWS, you could push it to a local MQT database, or you could do a WebSocket or TTP transfer. It doesn't matter. You choose, and then the beauty of saying using something like Azure is that's got very defined security standards, especially for IoT Hub. So we now get that security from the instrument or the sensor in the field all the way to our database on Azure via IoT Hub. I hope you found that useful. As per usual, please recommend this channel to your friends and colleagues, and I hope to see you again pretty soon. Bye for now.